All right. Thanks everyone for making it back. We're kicking off with 2 sessions in a row here now, and we have Izaak Meckler coming up from CODA, and he'll be introducing notes from the SNARKonomicon. I'm very looking forward to that very much. Welcome, Izaak.
Thanks. So, as I'm sure everyone's aware, SNARKonomicon, it's an ancient book of, eldritch magic. It was discovered in the 1500s. Okay, people don't like that joke. I apologize, this is in black and white. Also, my computer broke, so I couldn't do the color, but it would have looked even more terrifying. We're going to discover what is this SNARKonomicon exactly more in the talk, but I assure you it's not as terrifying maybe as the name sounds and as the devil on the picture suggests, but we'll find out. Okay, so just a bit about me and where I'm coming from. So I'm Izaak, that's me on Twitter. I work on CODA, which I'll say a second about, and also Snarky, which is a zkSNARK programming language, which we'll talk a lot about such things in generalities. So CODA is a cryptocurrency that uses recursive composition of SNARKs for blockchain accessibility and scalability. So accessibility meaning basically anyone can verify the entire state of the chain, even on a phone by checking a SNARK. So if you saw the first talk, it's sort of a similar concept. You can kind of compress down the entire blockchain by using SNARKs. So I've written probably, I think, someone can correct me if I'm wrong, but probably as much SNARK code as anyone else. And this talk is an attempt to distill some of what I learned. This is of course drawing on the work of many people, but I hope you'll learn something. Let's get started. Maybe just to get a sense of the audience, who has programmed a SNARK? Okay, great. So almost everyone will learn something. And who even knows what I would mean by SNARK programming? Okay, maybe more people have some sense. That's good. Maybe this thing is mind-numbing for. No. Let me not say that. Maybe some people have seen almost this exact slide on everyone else's talk before. So if so, I apologize. But just to set things up, let's say just to kind of say what do SNARKs actually do. For a given program, P, with, say, 2 arguments and a public value X, okay? What SNARKs let you do is they let you prove statements of the form, I know some secret Y, so that if you run P, my program, on X and Y, it will output 0. Okay, that's what SNARKs let you do. In such a way that the proof is, well, first of all, it reveals nothing about Y, so it's zk, zero knowledge, right? It's small, so like less than a k. If for a Stark, maybe you can ask, but and easy to check. So the verification time is on the order of milliseconds in practice. So then what we said here, program, right? Program P. Well, it's a program. What programming language is it written in, right? A program means a program in some programming language. Maybe it's x86 assembly. Who thinks it's x86 assembly? Anyone? Huh? Ah, yes. Well, perhaps on some level. C, maybe. Python? No, I don't think so. Haskell? No, it's not Haskell either. It's actually something else. And what is that something else? So, just to kind of say, like, SNARK programming, it's programming. It's programming this function P that we saw a few slides ago. But with a different machine model than all of the languages on the previous slide. Okay, so usually you think about, at the end of the day, it's going to be running on a RAM machine, right? A machine with a CPU that goes to memory, that does its fetches and computes, right, step by step like that. But in SNARK programming, you have a different machine model. Just a note about terminology. We usually people often talk about programs, or really what they mean is like a computer program. Meaning a program which is intended to be executed on a CPU. SNARK programming just means a program which is intended to be executed, for whatever that means, on SNARKs, okay? And of course, anything can be executed on anything else, but it's somehow about the attention. Just, let me say, most of this is not really specific to SNARKs. Some of it is sort of, but most of it also would apply to something like a bulletproof or like SNARKs. Okay, so it's just about the ideas here of how you think about the conceptual models of programming, mostly, and some of the tricks. Okay, so what about SNARK programming is different from quote-unquote normal programming, or as I call it, CPU programming. No, I don't call it that, but programming. Well, one is the cost model. So what is it that's efficient? Two is, in SNARKs you have this magic superpower, which is called non-determinism. Don't worry if this is a scary sounding word, or if you don't know what it means, I'll talk about it. And the third is that you can only inside of a SNARK somehow access a small amount of data at a time. In a way, it's not so different from a CPU. A CPU is this like tiny thing, and over here is like the giant memory, and the CPU just sees a small amount of the memory at any given time, right? But in a way, it's not so different. So let's first talk about the cost model. And in terms of what primitives, what are the sort of efficient primitives that you have access to in both settings? So on a normal computer, who has programmed a computer? Oh, that's great. I mean, it's not every room that you're in that almost everyone raises their hand, so that's great. So in a normal computer, what do you have? You have like, say, plus and times mod, 2 to the 64, say, 64-bit ints. You have memory access. You can load and store from memory. You can do bit stuff. So, and or and all that. And you have conditionals, jumps, basically. SNARKs, what's the deal? So, well, first of all, you have plus and times mod some large prime p. It's not so different, somehow. The p is a bit larger, but anyway. This is really important. Plus is like kind of free-ish. Okay, so plus costs 0-ish. When you're programming, this is how you think about it. Plus is almost free. Times cost 1. Does that make sense? Addition is like free. Times is not free. Cool? Make sense? Okay. And okay, what else you have? Well, no, actually, that's pretty much it. So you might be a little bit worried and say, oh no, really, that's it. You might say, well, this seems really bad. And this is the SNARKonomicon demon who is laughing at you. You only have plus and times. And sometimes when I think about this situation, I go back to this famous painting of Hieronymus Bosch from 1575 called SNARK Programming, ? Which illustrates some of the interesting aspects of SNARK programming. You see here you have the large prime, and here is the multiplication. And you might look at this picture and think it looks a little bit scary. There's people burning and so on. But actually, it's not so scary. One, this place looks pretty cool. There's a giant person with a giant mouth. And two, you're allowed to do some other stuff too. I kind of lied. It's not just plus and times. For example, you have non-deterministic choice, which we'll get into, and you can sort of compute on values as normal as long as it's only sort of statically known things, which is actually useful. Okay, so yeah. So the goal of this talk is basically the following. It's to convince you and show you how to make this a comfortable and exciting place to live. Some of these things which look scary, like the guy with the big mouth, maybe actually he's a nice guy, for example. And the major takeaways will be the following. One, SNARK programming is both beautiful and fun, just like programming. Non-determinism is a really powerful technique, but it's kind of scary, and we'll talk about what's scary about it. And three, there are a lot of really great, cool ways that you can sort of do things efficiently just by using field arithmetic that you have in this huge field that aren't things that you could necessarily do on a normal computer. And I'll try to give some examples in Snarky, which is this SNARK programming language of the concepts that we discuss. And you could also think that, at the end, you will see this SNARK demon and not think that he's tormenting you, but actually you will think that you're laughing with him about how great and fun SNARK programming is. Just a word about notation. We'll fix this large prime p that you have addition and multiplication for. You should think this large, but in the talk I'll use 13 in examples. which for a human is large. But you should think of it as like 2 to the 256, realistically speaking. And a number in 0 to p, you call that a field element. Okay, people know this? Okay. Okay, so just like, let's look at a SNARK program. This is a really simple program. What does this program do? Well, okay, who heard about elliptic curves before? Oh, okay, a lot of people. Well, even if you didn't, it doesn't matter because they're extremely simple. They're just a set of solutions like x and y to an equation that has this form. Okay, cool. And you know, geometrically speaking, say over like real numbers is what they look like. All right. So this is just a really simple program that just does this arithmetic, right? We said we could do plus and times. Let's do plus and times, just to introduce the notation. So you know, I say a is 1, b is 4, whatever, and here's the function that just computes you know, the right hand side here, right? X times x times x plus a times x plus b. Okay, does it make sense? And this is saying this is a function, right? This is kind of like, looks like JavaScript maybe, ish. Yeah. Everyone with me, sort of? Okay. So it's a function. That's just to give you an idea of what the syntax looks like. Now let's talk about non-determinism, which is quite interesting. So who heard about non-determinism? I know I keep asking people. Oh, that's cool. So sometimes, as people might know, checking is easier than doing something yourself. Who has had this experience in their life? That they were able to check something that someone did and it was easier than had they done the work themselves. Probably everyone has had this experience. Unless you sit in your room all day and don't interact with other people, I would imagine that you checked what someone else did at some point in your life without doing it yourself. So everyone knows somehow this is intuitively true. And what's cool is that this non-determinism power that you have in SNARK programming, it lets you go from being able to just check something to being able to do it, which sounds pretty nice. I imagine we would all like to have this, this power. I guess that's called delegating responsibility to other people. Anyway. Let's have an example, a concrete example of what using this non-determinism power looks like to do a very simple computation. In some sense, it's the simplest possible computation. And that computation is dividing numbers. So if I give you x and y, and you can do multiplication and addition and nothing else, let's say, how are you going to compute x divided by y? Okay. Another way of saying this, you want to find some z so that z times y equals x. People see that you divide by y and it says z is x divided by y, right? Okay. So you just want to find a z where that's true about z. So one, I know it's a simple, silly example, but it's a really and a very important function. You need it to efficiently implement elliptic curve arithmetic, which you need for doing anything inside of SNARKs. Hash function, Peterson hash, signatures, VRF, recursive composition, the list, it just goes on and on. So let's give a deterministic algorithm. It's probably not the best one, but it's the easiest one to think of. For computing x divided by y. So what's the algorithm? Who knows Fermat's little theorem? Maybe fewer hands. Okay. This says that if you raise a number to the p minus 1 power, then it equals 1, mod p. Okay, of course. So it means that you can do division by doing multiplication in a finite field. You just multiply. You don't really have to worry about it. The upshot is basically you compute x divided by y by multiplying x by y to the p minus 2. Okay? So you can do division by doing multiplication. It's kind of cool, actually. But actually, it's not that cool because this is expensive. You have to do like 256 multiplications, roughly, to compute this exponentiation. And that's just for one division. So you might already be kind of like, SNARKs, not so good, huh? Yeah, this is definitely bad. But what about checking a division? So like, let's say if someone gave you z, right? How many multiplications would you need to check that z is x divided by y? Who knows? Huh? 1, right? Just 1. You just check that z times y equals x, right? That's it. It pins down z exactly. So that's great because in SNARKs you have this guess and check power, which is another way of saying you can do non-deterministic choice. You have a magic guess function It's magic. In Snarky, it's called exists, because you're like, this exists. It's like guess. You also have a magic check function, which lets you make assertions, which you can, like an assertion in normal programming. It halts execution if the assertion fails. It's like throwing an exception. And I call assert. So, diagrammatically, here's how you do a division if you can magically guess things. So you guess a z, right? And then you just check that z times y equals x, and then you return z. Does that make sense? Conceptually, I say, I want to compute x divided by y. First, I guess z by magic. And then I just check, does z times y equals x? If so, the assertion passes, I go to the next line, I return z. Otherwise, execution halts, and okay, that's it. So, just to do an example, let's say we want to divide 6 by 2. I guess, conceptually, you first think you're sort of making all possible choices. Z equals 3, z equals 4, whatever. And then you check each one. So, okay, 3 times 2 equals 6, yay. 4 times 2 is 8, not 6. So their execution halts. 5 times 2 is 10, not 6. So their execution halts again. And so, this is sort of the only branch that we take in reality. So, okay, just like let's crank through it. So, okay, we did 6 over 2, right, that was 3. 1 over 2, I guess it's 7. I'm going to guess that. And in fact, I'm right, because we're working mod 13, if anyone remembers from that slide way long ago. Because 7 times 2 is 14, which is 1 mod 13. How about 0 divided by 0? I don't know, maybe 0. That seems like a good guess. Let's check. Oh, 0 times 0? What is it? It's 0. Okay, great. So I guess if I divided 0 by 0, it's 0. Oh, what about dividing 0 by 0? Well, I don't know, maybe it's 5. Let me check. Oh yeah, 5 times 0, it's 0. So I guess dividing 0 by 0 is 5. So dividing 0 by 0 is 0. Dividing 0 by 0 is 5. Which maybe you think the snark demon is coming to haunt you again. And yeah, that is a little bit troubling. So everyone take this in, okay? This is like understand non-determinism. It's either, right? I mean, you sort of don't know what div 0, 0 in some sense is going to return. It could return anything which would make all the assertions pass. In particular, well, it could return 0 or it could return 5. You don't know. And you have to think about it that way when you're programming. So there's a few things you can do about this. You can add an assertion, basically, that says y is not 0, like the second argument, say. That would cost you an extra multiplication, so, not great, but still a lot better than 256, right? So now it costs 2 instead of 256. So that's pretty good. Another thing is you could change the name of the function from div to div unsafe and forget about it. And that's an emoticon. It's a sideways. Okay. So, just like to show you what this looks like in code, yeah, as I said, you have a magic exists function, and this is just how you write it. So you say, okay, guess z, so let z be, I don't know, guess, and then assert that z times y equals x, and then return z. Okay? So it's kind of what I said. Cool? Okay. How am I doing on time? Does anyone know? 10 more minutes. Okay, that's probably enough. Okay, so let's just, you maybe think, okay, very cool, you can divide numbers, great. When am I going to ever have to use this in real life? Non-determinism. Well, you will have to use it in real life. It comes up all the time. And to just revisit our previous example, you remember we had this, this was literally, this was the slide before. We had this elliptic curve, and we had this function f for computing the right-hand side. Here, x cubed plus a plus b. So what if, we wanted to start with an x-coordinate, like, here's something that you have to do in SNARK sometimes. Sometimes you have to decompress a curve point. Who knows what I even mean by it? It means you start with the x-coordinate, and if you look on this picture of an elliptic curve, corresponding to every x-coordinate, there's exactly 2 points on the elliptic curve corresponding to that x-coordinate, because you can solve for y. You just take the square root of f of x, right? Yeah, but it could be plus or minus, so there's 2. But the thing is, right, there's only 2, so that's pretty cool. So sometimes you just have the x-coordinate because it's more efficient, maybe. You don't have to have both the x and y to determine the curve point. You just need the x-coordinate 1 bit. So one thing that you would want to do is decompress a curve point. So given just the x coordinate, you want to compute both the x and the y. And in SNARKs, it's super easy. What do? You say guess y, okay? And then just assert that y squared is equal to f of x. Done. And then you just return x and y. Does it make sense? You guess, and then you check. You guess, oh, maybe it's y. Let me check. Okay, I checked. Yep, it was y. I return y. And so what you return here is only the y's which make this equation true. But it's a little bit scary because, you know, right, so it could be this y, but it could also be this way. So you don't know, is this going to return that one or that one? You would have to add more checks to pin down one or the other. But okay, whatever. Sometimes maybe you wouldn't care. So just like to wrap up, you know, takeaways about non-determinism. Yeah, when you're trying to write non-deterministic programs, you think more about specs than algorithms. So, you know, this is like a spec, right? I'm saying basically return at y where, you know, y squared is equal to f of x. You see what I'm saying? It's not really an algorithm. It's just a spec. It doesn't tell you how to find y. Another thing which, you know, I probably was clear, but non-determinism gives you essential efficiency improvements. So you can't write efficient SNARK programs without using non-determinism. I mean, I don't know, maybe someone will tell me I'm wrong, but no, you can't. But it's also really scary, right? So we saw this like div 0, 0 thing, remember? Where like, if you divide 0 by 0, it could be anything. So that's really actually extremely scary because you can't rely on anything actually about the output of that function. It's totally unconstrained, which means maybe you're just using division inside of an elliptic curve operation, but you know, at the end of the day, what it means is you sort of allow the attacker. I mean, you think in your mind always about a malicious prover. I guess I should have mentioned that. You always imagine there's a malicious prover who's trying to sneak bad values past all of your assertions. You see what I'm saying? So that division function is really scary because it lets them sneak whatever value they want through your assertions, which is potentially really bad. So you try to build abstractions that somehow use the non-determinism internally, but don't leak it if possible. So for example, with division, if you assert that y is not equal to 1, or not equal to 0, then you don't have to think about it anymore. You know it's sort of really a function. It doesn't have non-determinism. Let me say something about taking advantage of arithmetic. All right, 5 minutes. There's non-tricky techniques, and those are like using elliptic curve-based primitives that I think people kind of know about this by now, but you know, there's like the Peterson hash function, for example, which is like 20 to 30 times more efficient than like a bits style hash function, like SHA or Blake 2. And another non-tricky thing is just simulating integer arithmetic. So field arithmetic is sort of, you know, as long as you don't overflow, it's the same as doing integer arithmetic. But then there's also tricky techniques. So these are the things that, you know, make the SNARK devil smile, and that also make us smile. So for example, there's packing. Okay, I'm not going to talk about it, but then there's also this technique that I didn't really have a word for it, but I called it sum as search. The idea is addition is free, and we want to make use of that. So I'll give you the simplest possible example of this. Just something to take home with you, and later you can go online and read more SNARK programs and assimilate, you know, this idea, and you'll see it in multiple places. So bools inside of SNARK programs, we only really have field elements. So how do you represent a Boolean? Just with a field element which is only 0 or 1. Okay, it's a field. We have 0, we have 1. Okay, happy? Are we happy? It's maybe not the best representation for all purposes, but it's pretty good. So, you know, with this representation, everything's pretty easy to talk about. All the bit stuff you know and love from normal computers. The greatest hits, we got them all. It's 1 minus x, right? So because if x is 0, then 1 minus 0 is 1. If x is 1, 1 minus 1 is 0. So it's not, right? We got and. You know, it's just multiplication, right? Because 0 times anything is 0, like false and anything is false. And true is 1. It's true. So it's 1 times 1. Make sense? Yeah. Okay. And then, if you have not an and, you can do or, for example, with just De Morgan, I guess it's called. So, x or y is true if they're not both false, right? And then you can kind of say like any, right? So if I have an array of bits, I want to return a bit which is true if any of them is true. You see what I mean? It would be doing like b's of 0, the 0th thing, or the first thing, or the second thing, or the n-1th thing. Okay? And you just write, reduce, like functional programming. Does it make sense? Do people see what I'm saying? Okay. So this is okay. What's the total cost of this? Remember, we only care about multiplication. This costs n-1 multiplications because each of these ors here costs 1 multiplication because it's coming from this. So that's okay, I guess, but actually you can do even better. How much better? You can only use 2 multiplications regardless of how many things you're oring together. And what do? Well, you just take all your bits and you add them up. Okay? You just add them. Like, they're numbers, they're field elements, you can add them. And then you just check, you look at that sum, and you say, hey, is that sum equal to 0? Right? And if it's not equal to 0, it means one of them had to be non-zero. Right? Does it make sense? Do people see? Maybe it requires a moment of thinking. Okay. No. No? Okay. So this is great because this only costs 2 multiplies rather than n-1. They're inside of equal, but I won't show them. So this is, maybe after. So this is, a neat trick. You're kind of searching the whole thing by adding everything up. But addition was free, so it doesn't matter if you add up everything. It's free. Ish. So, I'm almost out of time. Let's see. Yeah, so some important things that I wanted to talk about but couldn't talk about. One is it's one thing to write exists, to just write guess, but you actually have to find that value because it's on a magic computer. As someone back there said, it is executing on a normal quote unquote computer. So you need to actually specify how to find that value. This maybe someone would call witness generation. And the other thing I didn't talk about is how to simulate large memory banks. Remember when I was like, oh, you're a small CPU and the giant memory is over here and you need to reason about it. So I didn't talk about how to simulate that. That's an interesting technique. There's a lot of cool efficiency hacks you can do there too. But I also didn't talk about mixing SNARK code with normal code. It's another another important thing. And that's pretty much all I have. So thank you.
We have time for a couple of questions.
Yes, hi. Thank you for this very interesting presentation. Is there an intuitive explanation of why addition is so cheap and multiplication costs 1?
Let's see. Right now I'm simulating like the whole reduction in my mind to think about where it happens. I don't know. It's a very particular artifact of the construction, I think. But addition is always a lot easier. Maybe it shouldn't be so foreign because addition is always a lot easier than multiplication. It's kind of a cop-out. But we'll talk about it after, and I'll trace through the reduction and remember where it happens. I don't remember off the top of my head.
Other questions?
The reduce example, when you use sum instead of multiplication, it could still overflow, right?
Could it? So P is, let's say, the prime is like 2 to the 256. So you're adding up like, how many bits would there have to be for it to overflow? Like 2 to the 256, which is not a real number. I mean, it's according to some people, it's an actual number, but it doesn't exist. You would never construct that many bits in the universe. Let me say it that way.
Right.
Yeah. So you do kind of hacks like this where something is sort of okay, but only for cryptographic reasons, I guess.
I'm curious, like in your current circuits, what percentage is Booleanity checks, and if you have a smart way to aggregate those?
What percentage? I mean, it's definitely a lot, because most of it's the Merkle. Probably everyone knows the worst thing is doing a Merkle lookup. The worst thing is doing a memory load in a SNARK. That's like, I guess it's the case with real CPUs too. That's the worst thing. But I don't know percent. But yeah, that would be. I don't have a smart way. That would be great.
How do you test to make sure that there's no problem in non-determinism?
Yeah, that's a great question. No. That's really a great question because, as I said, it's really scary. The SNARK daemon sometimes haunts me in my sleep, thinking like, oh no, did I put enough constraints? But yeah, I mean, so we do unit tests. You can kind of just try and stuff values in there and see if you can make the constraints pass. Obviously, that's not really going to cut it for most cryptographic applications because there the errors are like on points that you would never find if you're testing randomly. But we've started a little bit looking at doing some formal verification, so like doing some calc proofs, but that's in early stages, and right now it's you get a lot of people to read the code and think about it very hard. The other thing is I always write pen and paper proofs, or in the comments I put proofs, but that can even only get you so far.
I think we have to wrap up the questions and move those to the coffee break afterwards and start preparing our next speaker. So thank Izaak very much again.
Oh, I just wanna go where love is alive. So I'm gonna do that. I just wanna go where love is alive. I just wanna go where love is alive. All of the chaos surrenders, changing the currents and tide. The water can keep getting deeper, 'cause I'll be right here staying dry. Ooh, yeah. I'm feeling it. Ooh, yeah. Come to me quick. I just wanna go where love is alive. Love is alive, love is alive. I just wanna go where love is alive. Love is alive, love is alive. I really don't have to prove it. I'm afraid there's no way to lose it. Oh, I just wanna go where love is alive. So I'm gonna do that. I just wanna go where love is alive. Love is alive, love is alive. I just wanna go where love is alive. Love is alive, love is alive. I really don't have to prove it. I'm afraid there's no way to lose it. Oh, I just wanna go where love is alive. I just wanna go where love is alive. So I'm gonna do that. Ooh, yeah. I'm feeling it. Ooh, yeah. Come to me quick. Ooh, yeah. Ooh, yeah. Just wanna go where love is alive. Love is alive. Love is alive. Just wanna go where love is alive. Love is alive. Love is alive. I really want to prove it. I'm afraid there's no way to lose it. Oh, I just wanna go where love is alive. So I'm gonna do that.
let's get going with our next talk. So we'll welcome up Harry Roberts next to talk about programming zero-knowledge proofs and digging into these high-level languages for doing this programming.
So I'm Harry. I've been working on Ethsnarks for the past year or so. And one of the biggest problems I've found is people don't like programming low-level SNARKs. And I wanted to look more into the challenges of high-level languages and making it accessible to people. So I'm going to go through some of the history, and slides and notes and stuff will be at the end. So I'm going to go through some of the history and some context about what the difference is between SNARKs, multi-party computation, fully homomorphic encryption and computers. Then look into, like, if you are making a high-level language, how would you compile something you're familiar with into this sort of low-level structure? And try to give a sort of a timeline of where we've come from, where we're going, and then give you a really good overview of all of the different high-level languages that are available if you want to do programming with SNARKs. So I want to start with this side. This is where I think we are with the industry as a whole. It's not very mature, but it's really interesting, and there's lots of interesting stuff. And of course, the slide that everybody has to have is, well, what are SNARKs? What are zkSNARKs? And the biggest thing for me is that they're compatible with Ethereum. They've got optimal proof size, and they're really quick to verify. So these three things sort of really make it useful for me. And of course, there's lots of research, privacy and anonymity, computational compression. But if we look at more of the history of, so with regular computers, we've got 50 years of research into compilers, optimizers, and languages. With MPC and fully homomorphic encryption, we're working with the same kinds of contexts. We've got binary gates, and you've got the sort of universal gates that from there you can construct anything else. But with SNARKs, it's a new domain. It's relatively young, and everything's different. So everything that we rely on, all of the history, if we look back at the history of where do we come from with regular computers, we're building on the shoulders of giants. So we've got Boolean algebra through the digital logic and circuit synthesis, and then the branch of modern compilers and optimizers, and that's going back 150 years or so. And at the bottom here, we've got like a big history of thousands of years of algebra, and then SNARKs. And a lot of it's relatively new, and we're trying to find common bits between these, so that instead of developing this stuff from scratch and making all of the same mistakes, we can rely on a very rich history of like formal logic analysis and modern compilers and optimizers. So yeah, we want to rely on the history of computer science rather than making it ourselves. But for that, we need to understand a bit about what is the low level and why is it different. I'm sure in the last set of slides he's gone over some of these differences, but I want to walk through a problem or two and show you, like, conceptually why is it different. And of course, I'm only going to be focusing on the small program and circuit part, which is if you've got a program, or if you've got your normal way of thinking is to write sequential programs. And how do we translate that into a circuit that fits into this big diagram? And I'm going to be focusing specifically on, if you look at the model of a regular compiler, how do we go from whatever your front-end language is to generating code and then optimizing it and transferring it to the lowest levels? So if we start off with a really basic example, on the left you've got a sort of procedural program, then you've got the circuit representation of it, and then you've got the sort of mathematical equation. And what we're doing is translating everything into a circuit where you've got a set of variables which are constant and immutable across the whole program. And with a regular compiler, we'd call this a static single assignment, where every single state of every variable is a distinct global state. And you don't have state, you don't have, you can't modify variables. So instead of overriding an existing variable, you're creating a new variable. So we go through, you've got A, which is 10. We've got B multiplied by itself, which is C. And then you add A and C. And instead of getting A again, or overriding A, you end up with A prime, which is its own distinct state. And as a whole, breaking the program down from the representation on the left into the representation on the right is the sort of first step you'd go through if you're trying to compile a language. So we go through a slightly more complex example, which highlights that, as you remember, additions are free. But how to put it? There are also different concepts from computer science that we can rely on. For example, instead of having a for loop where we're overriding the value of y with the incremented version or with the value of the array, we're really reducing the addition function on the list to create a sequence of outputs which are distinct values, where the last one represents the sum total of every item in the array. So the problem is we don't have any loops. We don't have any if statements. Everything's always evaluated. All variables are immutable. And as you said in the last talk, we only have these add and multiply operations. So you have to translate every problem you could possibly want to program from the representation on the left into these circuits, where the entire circuit, you can't have an infinite loop, or you can't have a non-deterministic loop, because you have to draw the entire circuit, and you have to be able to look at it from a high level, and you've only got a limited amount of space, and that could be, say, a couple of 100,000 operations or 1 million or so. But if you were to add an infinite loop in there, you need an infinite amount of space to draw the circuit upon. So this is the process of flattening code, where you're taking a set of statements and then turning it into the flat, almost visual representation of the circuit, where everything that it could possibly do is known. And the next thing you need to do is to evaluate it, just like a real circuit. This is the processor or the die that you're working with. So anyway, you've created these circuits, and you've got your add gates, your multiply gates. They're strung together. But how do we convert them into constraints? Well, first we should probably know what constraints are. Essentially, you've got a multiplicative operation there. You've got A times B equals C. A linear combination, which is the sum of terms, and each term is a variable multiplied by a constant. So with your circuit, you've got lots of different variables that you can rely upon, but they only have one value. But the circuit can also have the built-in sort of hard-coded values, which are the constants here. So if it's just a piece of Python code here that if you want to run, you can, that it sort of accurately represents the system or domain that you are going to have to work in. So if we look at how do we take one of these circuits and transfer it into, or convert it to constraints. So if you have the B squared operation, where you multiply B by B and you end up with C. But then in the yellow, I've got these built-in constants, or the sum, or the non-variable values that are sort of built into the circuit. So I've got 10 here, which is a constant. And then you translate that into the left-hand argument of the constraint, which one of the interesting things here is that because you're taking, I don't know how to describe this actually. Okay. So anyway, this is the process of converting a circuit into a set of constraints, where at the end you have 3 different operations. You've got the 2 multiply operations and the 1 addition operation. But instead of translating them into 3 different constraints, you can condense that down into 2 constraints, where the set of constraints verify that your circuit is operating as you intended it. So rather than evaluating each of the operations by themselves, you're saying that if I plug in all the values of the variables, then the only values of the variables that will be valid are whichever ones that match the set of assertions here. So if we take a more kind of complicated example, we're looking at if you want to translate an algebraic expression like this into a set of constraints, you need to first find what are which operations are multiplying something, and split them out into their own common sub-expressions. So because with a constraint you can either add a set of things in one of the terms as a linear constraint, or you can multiply 2 things together. So you're constrained by the multiplicative complexity. So if you can only multiply 2 things together, you need to break these out into multiplications and then find the sort of common expressions and common terms there. So we can take these out, and then we have a constraint for each of the multiplications that occur in the equation, and then we can multiply those intermediate values by each other to create the next expression. And then at the end, we end up with this sort of more complicated constraint down at the bottom, which ties those all together and says that if we take 1 plus d times x, y, whatever, then we're saying that a point that is, if you take the x and y of 2 curve points which have been added together, and you fill in all of these intermediate variables, then you can verify that it's only those 2 curve points could have been added together, and they must be valid curve points as well. So I guess the sort of high-level view of this is you have the secret inputs and the public inputs, and you're trying to compile your program down into a circuit. And from the circuit, you generate the constraints, and you also evaluate the circuit to create the variables, which ends up at the sort of intermediate state, which is inherently linked to the proving key and the proof. And then from that, you create the proof. So I've tried to give a fairly bad overview of like what is the lower level. But the sort of high-level points, you can get away from those. There are lots of really interesting techniques for optimizing if you understand the form of the constraints and how to translate your high-level problem in a way that you are used to programming into this different model. And also verifiable computation is a bit of a paradigm shift where it's completely unlike sequential programming. You have no state. You have to constantly rethink of your program as it were like a circuit board, and everything is wired together. And also lots of interesting things where like high-level algebraic concepts are quite easy to transfer over to this model, but if you're working with bits and bytes, that could be 200 or 250 times more expensive than doing something like this, where instead of 6 or 7 constraints, you end up with maybe hundreds or tens of thousands in order to do something that's very similar to how your computer would do it. So next I want to give a sort of overview of like what is the high-level languages that are available. So if you want to start programming with SNARKs, and you're only familiar with like normal high-level programming, you like Python or C or BASIC, whatever, I'm going to go through a handful of different projects which provide you these sort of frameworks or compilers or interesting starting points. And one of the simplest ones is called zkSNARK, where you've got a very, very simple language that it's very close to the constraints. So you've essentially got multiply operations, variables, functions, additions, and you don't get much else. But if you can translate your problem into that, then you can use it to do anything that SNARKs can do, but it will be very verbose. I'm not sure if it's Ethereum compatible, but it does the flattening and it's maintained. So another one is a very simple language where they've taken tried to represent the low-level constraints in a Lisp-ish form, where, again, if it's very low-level, but if you can convert your high-level idea into a very limited subset of the language, then you can do anything that SNARKs can do. But it probably won't be pretty. I'm not sure if it's maintained, and it's not Ethereum compatible. Then we've got Snarky, which was mentioned in the previous talk, where it's essentially a camel library where you can do lots of interesting, you've got full use of the whole range of camel higher order types, and you can do interesting optimizations because of that. And it's Ethereum compatible. It uses libsnark as a backend, but it's also maintained, and it's got lots of really good libraries for it. Like, you can use all of the libraries that are written for Camel, and it might be able to spit out constraints and snark code for you. So, for example, you've got the array reduction, you've got tree structures, and it might be interesting to see how far can you go with that, and how much of Camel code can you reuse that also happens to be Snark compatible. But the more interesting thing for me is it more accurately represents the process we're used to with regular compilers, where you've got a C source file and then the Pinocchio compiler, which converts into an intermediate format, which is kind of similar to like a SNARK-specific assembly language, and then spits out these opcodes here. The problem is it's a very academic project, but they broke new ground in terms of how do we make this accessible to developers who want to write a zero-knowledge SNARK program but don't want to have to deal with a low level. And they tackle this by giving you a C compiler. So the C compiler, if we look through, we've got the instructions that it emits take the form on the left, and you can see a circuit representation on the right. And for each of these instructions, instead of being these non-deterministic constraints, you can evaluate them like their assembly language. And as they're evaluated, they will fill in the intermediate variables and also emit the constraints. So you can compile your C source code to this intermediate language and then provide maybe like the binary version of your program, and somebody can execute that without needing the source code or the compiler, and then from that generate the witness or create a circuit or create a proving key or whatever you need to do. But they came across one problem, which is writing a C compiler from scratch is not an easy problem, especially if you want to be compatible with everything and the 30 to 50 years of C source code out there. So Geppetto, which is by the same people, as their next project was to reuse LLVM. So if you take LLVM, we're building on the long history of sort of commercial grade compilers, of all the insights into optimization, all the literally hundreds and millions of man hours of work that's gone into LLVM. So they don't have to write the C compiler themselves. But they next had the problem of, well, how do you translate the intermediate language that LLVM emits and then convert that into R1CS. I'm not going to go into details, but the source code is available. It's written in F# and some of the C++, and it does a reasonably interesting, good job. But it doesn't give you access to all of the interesting things that SNARKs can do. So you don't have native field types. So you're never going to be able to get as efficient as if you had have constructed the constraints yourself and worked around working with prime fields. And everything's written in bits and bytes, but it does a good job. And then the next thing we have zkSNARK, where it's a high-level language that looks kind of like Java or JavaScript, and it allows you to do really, you can write, for example, you've got RSA secret key knowledge, where they've created abstractions for you so you can deal with 2,000-bit numbers. You can deal with prime fields. And it hides all of that neatly it hides all of it neatly away for you, and is a very good optimizer. So this is a very promising project. It's also Ethereum compatible, and it's maintained. But you need to have an IDE in order to be able to write the source code for it to understand what you're doing. Then there's the Pepper project, which took inspiration from the Pinocchio project, where they wanted to create a C compiler that can translate into constraints, and they started off with this sort of initial project. And they've since worked through Ginger and Zata and Allspice and Pantry and Buffet and Zebra and Giraffe and onto Pequin, which is the sort of latest version of them. And through this sort of history, each one has been an academic project where they've been trying to solve a significant problem. For example, how do you have a processor that can, how do you synthesize a processor that you can verify that's been run, and so on. So generally speaking, you've got an interesting optimizer, you've got good C language support, and you can take functions like this and then convert them into a zkSNARK circuit and evaluate them. And a lot of people seem to be having this makes it very easy for them to pick up, write in a familiar language, and then create zkSNARK circuits and programs that are Ethereum compatible. But one of the problems that was similar with Geppetto and with Pinocchio is you don't have access necessarily to the low-level field types. So many operations you're using are still doing bits and bytes, but it gives you structures and arrays and all of the stuff you expect. Another interesting project is you've got CirCom, which is a JavaScript library. It separates constraints in evaluating the code, so you've got a set of constraints and it's very easy to pick up. And then you've got Socrates, which, again, you've got conditionals, loops, arrays, a Python-like language, optimizations, and Ethereum compatible. None of them are really ideal, though. But I was trying to think, what is a good ideal? And essentially, it's to split the different projects into their abstract components so that we can hit all of these goals and be able to reuse some of the things we want to do. But if you want to use zkSNARKs with Ethereum, I'd recommend these 4 projects here. But one thing we're missing is how do these projects work together? And essentially, they have no intermediate language. It's very difficult to reuse advances that one project has made with another project. And yeah, I'd just like to say thank you.
We have a little bit of time. We can take 2 questions if we have any. All right, then let's head for lunch. Food is served right outside.